Good morning, everyone. Yeah, if you can hear me, kindly unmute yourself and yeah, let's just have a chat for 30 seconds. So, good morning, everyone. Can you all hear me?
Good morning, sir. We can hear you sharp and clear.
Yeah, good. Trust our weekend is going on fine, and I'm sure we must have gone through what we did last week, the recordings and the presentation slides. I'm sure you must have gone through it. And like I mentioned, if you have any question to ask, the WhatsApp group is there. You can drop it or you can chat me privately, then I will attend to it. All right, so without wasting much of our time, let's quickly go to what we have today. Like I mentioned, we are treating two topics today, BOS and PV diesel. All right, so like I mentioned to you, BOS simply means balance of system. That is the meaning of BOS. All right, so for those of you that likes reading textbooks, if you are not seeing BOS there, you will see BOP. BOP means balance of plant. It's still the same thing. All right, so now what I mean by BOS is the accessories, all right, the protective devices that are needed for PV system to perform optimally. All right, because we are treating C&I, and your installation should run seamlessly without any breakdown. Now, remember, let me even tell you this. Remember, the capacity factor, or let me just put it like this: the utilization factor of your solar system is between 15 to 40, let's say 15 to 25%. It's not even up to 25%. What I mean by utilization factor is that the period in a day that you use only solar, remember, it is not 24 hours. I mean the generating equipment itself, which is the module. What is generating the power is the module, and it is not available 24 hours. All right. In fact, out of 12 hours, you can only enjoy it for 5 hours, depending on your location. So you can see that the utilization factor is very, very low. So once you have that in mind, you realize that you need to put some protection in place so that your system will not break down, so that you can maximize that 4 or 5 hours that the energy will be available from the PV module. All right, so it's just like maintenance. Your PV module, you don't do your maintenance when it is generating. All right, you shouldn't do that. You shouldn't do maintenance during the day, maybe in the afternoon. You need to shut. No, you don't do that. Your maintenance should be planned when it is not generating. All right, and that is because the utilization factor is very, very low. You understand? All right, so now I'm going to share my slide now. If you can see it, kindly use the reaction. If you can see my slide, kindly use the reaction. All right, so can you see my slide now? Can you see my slide? Can you see my slide? All right, thank you. All right, so now this is looking at today C&I solar PV BOS. That is the balance of system. All right, so basically the balance of systems are wires, DC cables, AC cables, breaker, surge protector, AC combiner box, bus bar, DC combiner box, earthing, lightning arrestor. But we won't be taking earthing and lightning arrestor now. By the time we start the design proper by April or May, then we are going to be looking at earthing and lightning arrestor. All right, because a lot of people take that for granted. It's part of the BOS. All right, and it is one of the very important BOS because your generation. All right, so it is very, very important as well. So we'll be looking at that now, and by the April or May, we are going to look at that. So these are the ones we are going to be treating today. We did the PV system and size the appropriate cable and protection devices for it. Now you keep hearing me mentioning power flow, power flow, power flow. What I mean by power flow is if you are generating your power from the PV module, it flows from the PV module to the charge controller, from the charge controller to the battery, from the battery to the inverter, from the inverter to that is the power flow. All right. Then we can also have another power flow that it is flowing from DC, that is the module, straight to AC. So once you understand that power flow, you'll be able to design proper, you'll be able to design your equipment properly and also the BOS. All right, Adeika, please mute your mic. Let's not, so that there won't be any form of glitches, because we are recording. All right. All right, please, Adeika, mute your mic. Sorry, your camera rather. Your camera, please. All right, thank you. All right, so now let's move on to the main thing. All right, so this is it. All right, so now let's move on. Now this is the meaning of BOS. BOS encompasses all the components of PV system other than the PV panel. All right, I mentioned to you that panel is the generating equipment. All right, so I can liken my PV panel to my diesel generator, because the diesel generator is the one generating the power. So just like we have diesel generator, we also have PV panel, which is the generator. All right, your battery is not a generator. Your inverter is not a generator. Which is the fuses, the enclosures, the breakers, the combiner boxes, the inverter, the charger, the battery, the bus bar, and the battery. All right, so yes. Are you with me, please? Are you with me, please?
Yes, we are with you.
All right, thank you. So now when you look at this, you can see a PV array. Can you see the generator in a PV array? Then we have the distribution box. Now inside this distribution box, this DC distribution box, I can call it DC combiner box. All right, remember, like I mentioned to you, I'm not keen about textbooks definition. Just understand what you know. Just understand the basic. Once you do that, then you can bring out your own definition. All right, so like I mentioned, this DC distribution box can be likened to a DC combiner box. So when we then you have another one, then you have an electrical grid. Now, I need someone to tell me, is this an off-grid system? Is it an on-grid system or an hybrid system? Who can tell me? We did that last week. Is it an on-grid system? Or an hybrid system? Or an off-grid system?
On-grid.
On-grid.
Controls.
Is it on-grid or off?
On-grid system.
This is an grid type system. Another name for grid type system is what? Grid connected system. All right. So and the reason you can see the inverter here, this inverter here is an on-grid inverter or solar inverter or PV inverter or grid tied inverter or grid connected inverter. All right, so this is an on-grid system. All right, so now let's move on. I won't take any question for now. Let's finish this first. Now looking at this as well, this is also another system. All right, so now when we look at this, is our solar panel. This is our solar inverter. This is our switch box. This system is what?
Off-grid system. Off-grid.
Hybrid. It is hybrid.
It's an hybrid system. I want to see that next week. we're going to see AC and DC coupled system. So once you understand AC and DC coupled system, then you'll be able to understand this. But looking at this, you should know that this is an AC coupled system, while this is a DC coupled system. But don't worry, when we get there next week, you understand it. But the main thing that I want you to get is ensure you understand the flow. When I know that the power from the solar panel is entering the solar inverter, and I know that the current is direct current, if I'm going to size the circuit breaker, the surge protector, I will size based on the understanding that what is flowing from the able to once the flow will be able to size appropriately. All right, so now let's move on. Now let's start with the main one, which is what solar wires or cables. Now solar wires or cable is one of the very important POS in PV system. All right, the reason why it is very, very important is simply because if you don't size this properly, the installation might lead to disaster. All right, it might lead to fire outbreak. And remember, you are installing your system within the facility of the business owner. So it is not only your investment that is going up in flames. The business owner is also susceptible to solar wires. It is good for you to size appropriately. And I'm going to show you the industry standards. All right, the industry, which is the IEC, for you to be able to size appropriately, and we're going to match that up with a cable catalog. All right, so you need to pay attentively. All right, now there's a difference between wire and cable. I'm sure you know that. Now a wire is a conductive material that is usually made up of copper or aluminum, both of which have a very good conductivity. But all right, that is a wire. A wire represents one core. Now, a cable is a group of two or more different wires that are twisted or bonded together, surrounded by an insulated that is a wire. All right, but if I have more about a cable, so you should understand this for the project managers so that you can communicate effectively to your team members. All right, so if you are telling them, bring size this cable, they'll be able to know that, okay, it's either two or three wire, one core. Is that understood? You should be able to identify the difference between the two of them now.
Yes.
All right, so now let's proceed. Now, solar installation, especially the DC cable, which is the solar cable, ensure you identify all these characteristics. You don't use any other cable. Now, your normal AC cable cannot be used in place of a DC cable. All right. And because of all mentioned here, which is not exhibited by the normal AC cables that we use. All right. Now, solar cables is a cable type specially designed to be used in a PV solar system. The cable is designed specifically for that system, and we're going to see the reason. Now this cable travel of ambient temperature. The cable is going to be an outdoor cable. It will be outside for longer period of time. It can be 30 years, depending on the warranty of the PV module. All right. So cable should be able to withstand the harsh weather condition. If it is snow, it should be able to withstand it. If it is raining, it should be able to withstand it. If it is hay, it should be able to withstand it. All right. Now the cables are suitable for permanent outdoor long-term use on climate condition. So the cable should be able to withstand it, and it is not all cables that can withstand this. So if you are procuring cable for C&I installation goes specifically for solar wires. And we have a lot of that the expected period use is 30 to 40 years or normal usage condition. All right. Now halogen free, make cable jacket and insulation resist highly flame resistant. So that's the key. Now let's now keep moving. It's getting interesting. So now, how do we select solar cable? How do we select our solar cable? How do we select ours? Now, when selecting a suitable cable for your solar installation, the full factor and no correct. I've seen cable catalog where they will tell you in air or in ground. I'm sure you must have seen that before. Right? Because okay, inside the ground is different. If you're keeping on that, the lot of factors that you there are a lot of us that this is what the derating factor is all about. Now, derating factor are factors that may affect the cable's ability to withstand rated currents. All right, the cable's ability to withstand the rated currents. All right, so now this include ground temperature, air temperature. I should show you see so that you will see what I'm talking about. Let me show you the derating cable. Every cable catalog has their derating. You need to check cable. You need and this. I'm going to show you. Share my screen. I'm going to stop this now. Let me share. I'm going to show you the rate facts. All right. Let me show my entire screen. Can you see my screen? Can you see my screen? All right. So now this is cable catalog from Polycap. Can you see it? Can you see my screen? Can you see the catalog that I'm showing you?
Yes, sir. We can see very well. I can see.
All right, good. So can you see rating factors? Can you see rating factors for variation? If that means if I'm suspending my cable, I'm not passing it under the ground. All right, there are two ways in which you can route your cable. It's either you fly it in the air or you bury it in the ground. So now if I'm flying my cable in the air, I'm going to consider this. You can see ambient air temperature. Can you see it? Ambient air temperature. So you can see degrees of. So that means that the ambient temperature in which I'm like in degrees Celsius, use this derating factor 1.15, 1.14. If the temperature is 30 degrees, I'll use 1.10. If the temperature is 35, I'll use 1.05. If the temperature is 45, I'll use this. Can you see it? Do you understand this? Do you understand this? Now look at this. If you are going to bury the cable under the ground, if the temperature inside the ground is green, I'll use 0.91 as my derating factor. All right. Now, rating factor for variation in ground temperature for cables in duct. I'm burying the cable inside the ground, but I'm not just burying the cable and it inside a duct. Duct makes pipe. I'm passing it inside the pipe. All right. So what is going to be the maximum temperature I'm considering? Because when you are putting your cable inside the duct, obviously they need to factor in temperatures of for that going. All right. Which cable am I using? If I'm using up to 25 mm, is it single core or multi core? All right. If I'm going to bury my cable, if I'm going depth of 7 and I'm saying single is up, then I'll use 1. Do you understand what I'm saying? But if it is above 25 mm, but up to 300 mm, all right, and I'm going, let's say 2 meter, which is 2000 mm, then it is a multi-core, then I will use 0.91. You can see can you see it? This, if I'm to see. So my residence stand, all right, do that now in by the durating factor. But don't worry, you go back to my slide. So my slide now, calculate the overall derating factor. Calculate the overall calculate the factor of 3 kb centimeter. This is the each other. The barrier is 1 meter underground at a temperature of 15 degrees Celsius. Can you see it? Can you see the spacing is 15 centimeter? All right. Now, when you check your catalog, then you are going to see all this. The ground temperature for 55 degrees Celsius. Let's see if we can see that. Ground temperature, we are going to bury it under the ground. Let's see temperature for 55 degrees Celsius. For 55 degrees Celsius, let's see. Coming. All right, so for 55 degrees Celsius, the ground temperature is 0.8. This catalog does not factor it, so you can use a catalog that factor. So now let's see, then the barrier depth is 1 meter. This would be the durating factor. Then grouping factor, 3 cables spaced. You are spacing them 15 centimeter apart. So you have the factor of 0.78. So the overall derating factor is this. Now the reason why I had to take you all through this derating factor is simply because everybody is a victim of this. If you are not a victim of this, I want you to raise up your hand. Now, everybody is a victim of this. We know that if we decide your cable point of doing it is to and overall derating factor. Now, if you're not a victim of that, let me see your hands up. If you've not been using the 0.8, let me see your hands up. I used to use 0.8 back then, but I don't use it again. 0.8 again. All right. That is the reason why at times you realize that after your installation, you realize that it gets to a point you use this overall derating factor. Now this is a cable. You can see this is the conductor, this is the insulation, this is the bergamot, and this is the insulation. All right, now let's move on. Now let's see selecting a suitable cable for solar projects. Now listen attentively with this. These are the steps. Now calculate the load current, which might be the short circuit current for solar module or pattern current. Now, if you're going to size your cable, if you're going to size for solar system, ensure the first thing is to know your, if I see cable from what I will use, that is what I will use. 0 point, right? And once you've done that, you now check the proposed cable catalog to match the cross-sectional area. All right, so now let's start. Let me go to a cable. Let me show you a module data sheet. Let me show you a module data sheet so that we can look at this. Let me show you this. Now, can you see my screen? Can you see JA? So I'm showing you a JA. So let's be practical with this now. It's DC cable first. Now, I will simply go to my cable catalog. Let me assume that I'm using 610. Can you see I'm using 610? Let me zoom in. I'm using 610. This is it. This is what I'm using. All right. Now, so for me to size the DC cable, remember I told you that for CNI, all right, CNI, if you are doing your installation for CNI, your major type of connection within your solar farm, within your array is stringing. You just connect positive to negative, positive to negative. So the series connection, series connection, all right. And remember what I told you, if the series connection, you increasing the voltage, the current stays the same. Can you still remember? Can you still remember? This panel I installed, or no, let's say I have 17 of this panel. I have 17 of this panel in my PV farm, in my solar farm. The VOC is 48.110, while the current is what 16.0. So now, if I am connecting these 610 in series, that the suffering, I need someone to tell what will be the current that is coming. 16.05. The current stays the same. It's only the voltage that will increase. What will be the voltage? The voltage will simply be 14.110 times 17. Are you with me? Hello, are you with me?
Yes, sir.
Carry on.
All right, good. So now we have the current. We have our current. Good. We have our current was 16.05 amp. It's not changing. It remains the same. All right. Now let's move on. All right. Now, if you are doing load currents, which is 16.0525, 1.25. Now you might multiply. Do you know the reason why I'm saying you might not multiply? Because it is already the short circuit current, and that is the maximum current that can actually flow from the from that aspect. Even if positive and negative should touch each other, mistakenly touch each other, the maximum current that can flow is 16.05. So if you feel like multiply with 1.25, you can go ahead. If you don't want to multiply, you are still on the good side, all right? So now the reason why I had to put that 1.25 is simply because if you are using formula to calculate, that is where we are going to see that. All right. So let's multiply. When you multiply 16.25, what will you get? Multiply this one times 1.25. What will you get? What will you get? We are multiply. What will you get? What will you get to? You get 20 now. 20 amps, right?
Yes.
All right. Good. Attend to a call. 30 seconds. I'll get back, please. All right. Sorry for.
Okay.
Now let's not count. All right. So now let's continue with the now. All right. Now you check the catalog to match the current carrying capacity. Remember, we have 20 amps. So now let's run the cable. There is still polycap. We have polycap. Can you see my polycap cable? This is strictly solar cable. Can you see it? Hello, can you see it?
Yes, yes.
All right.
Yes,
So
sir.
now good. When you look at this, can you see I have capacity. What do we have? We have 20 amps, right? We have 20 amps, right? So now we'll come to this side. Can you see the current carrying capacity? So this is the least cable the least current that I have here is what is 30. All right. But for solar, I know 1.5 or 2.5. Right? The reason being that for expansion, so it's advisable that we should start with 4 mm. Now is that the voltage is not going to higher. All right. So now let's move on. I'm sure you've seen this. So you can see the current capacity. You've seen the resistance in ohms. You've seen the tolerance. You've seen the diameter. So basically, what you need is just which is this. Can you see? You need the current carrying capacity and resistance. You need the resistance if you want to calculate your voltage drop. All right. So now so now we have 55. So now calculate the overall derating factor. All right. Now the reason. Now you're going to see the reason why. We have now the derating parameter can be gotten from the catalog of the intended cable to use. Now let's assume that we are using is a roof. We are doing just cables with fly in the air, right? Hello.
Yes.
Yes.
Hello, can you hear me? Good. All right. So now in the air, right? So now if it will fly in the air, what do you think the air temperature will be? What do you think the air temperature will be? Now all these things is just an assumption. All right. That's the reason why if you've been to the site often, you go to the site often. This is what the temperature. This is the depth that I'm going. All right. So now what is going to be the air temperature? The air temperature is, let's assume the temperature is let's say 45. All right. So for the air temperature to be 45 degrees Celsius, we are going to use a derating factor of what? Of 0.96. That's what we are going to use, 0.96. Now, what other factor again are we going to consider? What other factor again are we going to consider? We are not going to bury the cable. Are we going? Let's assume we are not burying the cable. So we won't use this factor. We won't use this factor. We won't use this factor as well. Let's move on. Factors, rating factors for depth. We are not using the depth. We are not using soil resistivity. Let's move on. We are not using soil resistivity. Let's move on. Okay, so now you can see DC cable for 2 core SRP. This is the voltage. Can you see the voltage? Oh, sorry. This is even the cables that we want to. Let's just move on. Factor so that the circuit of 2 cables. Now you are passing. Remember, positive and negative, yes. Right? Now you are going to group them. It's positive and negative, so you are going to group them. So while you are grouping them, you are going to space them as well. Now, are they going to be touching each other? Are they going to be touching each other? If they're going to be touching each other, they're going to use this derivative factor. How many cables are going to pass through how many cables are you going to lay? Remember, this is ground, so we're not talking about ground. Let me move on. This is actually ground. You can see ground. It's no wonder all the groupies are in the ground. All right, so now since we have that, because even if it is flying in the air, we are going to pass it through a duct. Coming, I want to see a duct. This might possibly delay us. All right, so I wouldn't want this to delay us, but when you have the catalog, you are going to see it. But let me just assume that we are passing the cables through the ducts, and the derivative factor through the duct is, let's just say 0.83. Let's say 0.83. Now, if you consider another factor again, let's say another factor is touching each other. You understand? Probably they are not. You are spacing those cables between themselves. Let's assume that the derivative factor for this is 0.92. So we have all the derivative factors. So what you do next is to multiply. So 1.9 is 0.83 times 0.92. So once you multiply all these derivative factors together, you are going to have overall derivative. So when 0.96 times 0.83 times what? 0.96. 0.96 times 0.8 0.3. Is it?
0.7.
0.7. Are you sure?
Yeah.
That's
706.
0.0. Okay, let's do that. So calculate these steps. Calculate the overall derivative factor. Derivative parameters can be gotten from the catalog. You can see that we've gotten the derivative factor, right? Now, the capacity, the carrying capacity, what the CCC is. You can see the current carrying capacity. This is it. Now, when you multiply 30 times is 0.76. What are you going to get? 30 times 0.76. What are you going to get? That is what you're getting, right? Now let's see. Now multiplied, and we are getting the rated current carrying capacity. Now the value of age must be greater than the load current. Now, who can tell me what value of the load current did we get? Who can tell? Who can remind me? What value of the load current did we get?
20.
Sorry? What is it?
20.
it is 20. All right. Capacity is greater than this cable. The value must be greater. And what value did we obtain? 22, right? Must be greater than now. Let's assume that the derivative factor. Let's assume that we are passing the cable under the ground. Let's assume that it is a ground mount. And we are considering the burial depth. We are considering the soil resistivity. We are considering the duct derivative factor and the rest. So after multiplying everything together, you are getting is 0.5. Now when you multiply, it's 0.5 times 30. What will you get? It's 0.5 times 30. What will you get?
15.
15. You can see that 15 is below 20. See that. Now when you multiply it by 41, what will you get? When you multiply 0.5 times 41, to use this cipher. Now, if I use you multiply 55, what will you get? 55 times 0.5, what will you get?
27.5.
So you see that is more than that 20. So I can conveniently use 4 mm cable. I can conveniently do to know if you are going to use 4 mm is voltage drop. If the distance is more, all right, you consider voltage drop, and if it is not within range, then all right. The cable is soldered current carrying capacity is greater than the current carrying capacity, and match the current carrying capacity with the corresponding cross-sectional area. You can see that I've gotten 55, which is the current carrying capacity. So I'm matching it with the corresponding cross-sectional area, which is what 4 mm. Do you understand that? Do you understand that?
Yes, sir.
All right. So now let's move to sorry? You want to say something? Don't worry, let's not ask question now. Let's now see. We've talked about DC cable. Now let's move to AC cable. Let's move to AC cable. Let's see from inverter. I'm going to share inverter data sheet with you now. Now let's look at this inverter. Can you see my screen? Let me zoom out. Can you see my screen? Remember, your inverter is what is converting DC to AC. All right, so we've sized the AC, the DC cable, which is 4 mm. All right, we know how to size the DC cable. Am I right? Am I right?
Yes, you just taught us.
All right, good. So now let's see how to size the AC cable. Now to size the AC cable, you come to the output. You can see output of your. This is the inverter data sheet that I'm using. This is the inverter data sheet that I'm using. All right, so now since you can see input is the DC, so I'm not talking about this. This is the one I'm talking about. Output, which is the AC. Now you come to maximum. You can see maximum output current. Can you see? What is what can you see here? Maximum output current. What can you see? What can you see? 240.3. Good. That is it. 240.3. And remember, we have different types of cable. We have 2-core, 3-core, 4-core, 5-core. So now let me go to our, you can see 240.3. Now let me go to our data sheets. Let me go to our data sheets. You can see. Let me just do this. You can see I can decide to use, your inverter is what is a 3-phase inverter. So you can decide to use 1 core. You can decide to use 4-core. Now let's use 1 core. Let's go to 1 core. You can see, let's go to 1 core. You can decide to use aluminum. You can decide to use copper. All right. So let's go to our data sheet. This is the cable data sheet. You can see single core aluminum. You can see single core. Let's go to copper. Single core copper conductor, SOP. That's what I'm using. Now, what is the cable? What is the inverter? That is, what is it? 240.3 amps, right?
Yes.
Let's go to our current capacity. Current rating. This is our CCC. Current carrying capacity. This is it. Current rating. Can you see it? This is our current. Now, it now depends. Are you going to bury the cable under the ground, or you are going to fly it in the air? Anyone that you choose. Now, let's assume that I'm going to fly it in the air. What's our cable? I will start with this. You can say I will start with 269. You know why I'm starting with 269? Sorry?
Yeah, because it's surpassing the
maximum current of the inverter. That's it. Now I'm going to start with 269, but that doesn't mean I will use this 70 mm. That doesn't mean I'm going to use it 70 mm. Now it is after I've got to my derating factor. All right. Now let's now start. Let me assume that I'm flying the cable in the air. Let's assume that I'm flying the cable in the air. All right. Now that you know how to calculate the derating factor, let's assume that I'm flying the cable in the air, and the overall derating factor is, let's say, 0.65. 0.65. 0.65. So now, if I'm going to do that, that means I will start with 255, right? Because it's more than 240. Now, using 255, when you multiply, is 0.56. So it's 0.65 times 255. I'll give you what? Sorry?
Are we burying it in the ground or
we are going to do the two. I just want to show you something. We are going to do the two. Let's say let's say we are flying it in the air first. Let's start with flying it in the air. So you start with 269. So multiply 269. We are assuming a derating factor of 0. Let's use 0.7. For if you are flying it in the air, the derating factor is not that small. Let's use 0.7. So when you multiply 269 times 0.7, that will give us what?
188.3.
Sorry?
1.3.
188.3.
So now, do you think I can use this? Do you think I can use my cable 50 mm square? If you okay, sorry, do you think I can use?
I don't think so.
Why? Because the value that we have is less than the load current. What's the load current?
240.
Less than good. I can't use 9.7. What that will give us what? 240 times 0.7. That give us what?
168.
168.
240 times 0.7. What is it?
168.
168.
168.
Sorry, it should be 340. 340.
Oh, sorry, 340 times 0.7. What is it?
238.
238.
It is still lower, right?
Yes.
Yes.
So obviously, I can't use 95 mm. Can you say I can't use 95 mm? So once you get the rating factor, just trace it down to the cross section area. Now obviously, 0.7. That will give us what? 270. Is that right?
77.
So 277 is more than, you can see now. So since it is more than, then I can use 1/5. So the cable I'm going to use is what? Just trace it down. Is 120 mm. Do you understand this? So this is how to size your cable. So you can do the same thing for in ground. The same procedure as well is what you need. I'm sure you know how to size this.
Where did you say that one, sir? I'm just trying to see what you did. There was something you did. Because I'm getting lost a little bit now. I want you to come back. You multiply 340 by 0.7 and we got 238, right?
Yes.
So there is something you were pointing out, but I'm getting lost.
Okay.
You see, you wanted
Okay.
to go to the next one.
Okay. The 340, when you multiply the 340 by the overall waiting factor, the value you are getting is less than the load current, which is 240.3, is less than it. So that's the reason why I'm not going to select this cable 90. I'm not going to select 95, right? Now, when you move to 396, you are going to get 277, which is more than the load current. So since it is more than it, then I can select which is 120. Do you understand that?
Yes, sir.
So the same principle is applicable for a ground. So on your own, you can look at this. All right. So now let's move on. I'm sure by now you'll be able to size DC cable and AC cable. All right. DC cable and AC cable. So now let's move on. Let's move on. Now, in a situation where the calculated load, you're welcome. In a situation where the calculated load current is higher than the available current carrying capacity in the catalog. Now, what I'm saying is that now, do you know that you can have an accumulated load? Now, I'm going to give you can have an accumulated load current. Now, let me give you an example. Now, when you look at this now, what is the load current for this inverter? What is it? 240.3, right?
3, yes.
Good. Now, we've not done that, but we'll get there. Don't worry. But let's just talk about if let's assume you have 10 inverters, all right? 10 inverters, and one has these load currents, this maximum output, and everything is entering inside a combiner box. Remember, a combiner box, you will need to calculate the overall cable that is coming. Now, if 10 of these is entering inside a combiner box and they have a current of 240.3, what will be the overall current? The overall current will be what? 10 times 240.3. Am I right? And that will be 200403. Now, there is no catalog that you will see. Can you see? I'm opening the catalog now. Can you see in current in air? You can see you will see you have 2,000 plus. If you see one, even if you see 1,000 plus, you are not advisable to use this size of cable. You can see 1,000 is much. What do you want to cover situation? What you simply do is this. You can see in a situation where the calculated load current is higher than the available CCC in the catalog, simply divide the calculated load currents by the number of runs you intend to have. All right. You're going to now. This is it. From this now we've calculated what? Still on this example. What is the total current when we have 10 inverter? That is 2,403, right? Good. So just note that. Now let's go to the catalog. Now let me assume that I want to use 400. I see. Now let me assume when you divide, what will you get? Divide 2403 divided by 5. What will you get?
By 5.
Yes, divided by 5. What will you get? Sorry?
480.6.
480.6. Now when you look at 480.6, if I bury it in the ground, 480.6, it falls within this side, right?
Yes.
When you look at this, that's 447. Am I right?
No, sir. With 480.6.
It is higher than 440.
So that means it falls within 515. Am I right?
Yes.
assume the duality factor of multiply this 515 by the duality factor. What will you get?
360.5.
Sorry?
360.5. 360.5.
360.5.
Good. Now, when you notice that 360.5 good, less than that 4 something that we calculate, that's 470, right? It's less than that 470. It's less than it, right?
Yes, sir.
480.5.
Good. So now let's move to the next one. Let's move to 576. Multiply 576 by 0.7. What will you get?
403.2.
400 and what?
And 3.2.
Now, which is less than? Multiply by this 651. What will you get? That 651 multiplied by 0.7. What will you get?
425.
Yeah, multiply by 0.7. What will you get?
459.
459. So now, what I'm trying to get now is let me just explain. What I want to get now, when you divide, remember we've divided by 5. What are we getting? Yeah. We are getting what? When we divided that 2403 divided by 5, we are getting 480, right? Right?
Yes, sir.
That 480.6 is the maximum current per run. All right. So any CCC that we have must be greater than that 480. Now, when you multiply 427.7, what will you get? 427 times 0.7, what will you get? What will you get? 427 is more than, right? It's more than 480.
Well,
Is it more than it?
427 or 727.
If you multiply 651 is less than 480. But if you multiply 727 with it is what? More than 480. So this is going to select. I'm going to select 500. All right? 500. That is what I'm going to select. So in this case, it means that per phase, I'm going to have 5 of these cables. Do you understand what I'm saying?
Yes.
So anywhere I'm sure you must have been seeing some installation where they have per phase, you will see you see is simply how they've this is how they've calculated. So now when you divide, you're going to have maximum current per run, which you've just gotten to be what? 480.6. Now calculate the overall duality factor, and I've assumed it to be what? 0. Multiply factor with the current carrying capacity. We've been multiplying it with the ones that we have. But then it is the 727 that we multiplied with, and it's greater than the photo with DCC proposed cable to calculate the derated current carrying capacity. All right, the higher the value higher must be great. The value of K rather must be to calculate the DCC. You have a current that you need to calculate. All right. Let me assume you want to calculate. The truth that you need to calculate the current. I'm sure you remember P equals to I equals to P over W, and you still remember that's for single phase. Let me just write it down. You still remember P equals to V over I. From this, you can calculate your I. Your I equals to P over V. I still remember last phase. For three phase, your P equals to what? Your I equals to P over root 3, right? VI. V cos your power factor. You still remember this formula. So in case along the line you don't need to calculate the current, the load current, you can use this formula, then it by 1.25. All right. So let's get DC side battery cables. Now you write down the active power of the inverter, where the cable will be terminated alongside its battery voltage. Now you all know battery voltage is 44 volt current. The battery voltage to get the current carrying capacity of the battery cable, which is still the same thing as the load current. Now resistance or impedance. Now, voltage drop is the amount of voltage loss that occurs through a circuit due to its impedance, which is the same thing as resistance. Now, how do you mitigate voltage drop? When you realize there is a voltage drop, what do? You increase using a lower resistance material of conductor. Maybe you design using aluminum, you can use your copper. All right. Now, when you realize that the voltage drop is not within limit, that if you are using 4 mm and you cap voltage drop, you realize that when you increase the if you are using 4 mm, you use 16 mm. You try it again with the 16 mm. If it is not within range, go up again. All right. Now, increasing the number of conductor, we've done that. That is, if you are using one phase, all right, you can go ahead and use two. You can if you have one conductor per phase. When you increase, if you do, obviously there is if for example now the length where you pull a 100 meter, all right, obviously if you realize that the voltage drop is not within the limit, see how you can reduce the length. Once you do that, calculate the voltage drop, it will be within the limit. You can also mitigate voltage drop by decreasing the load currents. But I'm sure or if you realize that this equipment I'm using, this is what I'm getting, then you can go ahead and decrease the load current. That's the reason why in C&I, we don't joke with preliminary design. Preliminary design is very, very important. Preliminary design is very, very important. So in this preliminary design, you are going to consider all this. Right. So now, what is the formula for calculating voltage drop? What is the formula for calculating voltage drop? So this is the formula here. IMP times the resistance times the length times 100 divided by the total voltage. The resistance is the cables in ohms, while length is YL is the length of the wire. Now the total voltage is, I'm sure you know, for example, now the cable. Now, like this, now if I'm going to calculate the voltage drop for this, now let's look at this. Can you see my screen? Can you see my screen?
Yes, we can.
Yes, sir.
Yes, you can.
Now we are using this 410. The connecting distance is 100 meter. Let's assume that the distance is 100 meter. Now, and I'm connecting 17 of these in series. All right. Now, using that formula that I've shown to you, let me go back to the formula. Using this formula, my IMP, you already know what your IMP is, which is from here. I can decide to use IMP. All right, and see ISC, anyone you like, you can use. If I'm using IMP, then I'm going to use this to be my maximum voltage. But remember, this is the voltage that will actually get to. Remember this, your V maximum is the load voltage. I'm sure you know that. You can have your V maximum when it is operational. All right, so this is what I'm going to do. IMP is what? 15.34. Now, what will be my VMP? Remember, I'm calculating. I have 17 in series. So, what will be my total voltage? What will be my total voltage? 17. What will be my total voltage? Multiply. What will be my total voltage? 17 in series. That will give us what? That will give us what? Remember, I'm calculating. I'm multiplying. So the voltage, the current stays the same. So I want to calculate the voltage drop, and it's passing through
664,309. Oh, did I get?
No, 37.37 times 17. That was
Times
09. 76.09.
676.9. So just take note of that.
676.09.
All right. So just take note of that. Now remember, initially we've selected what? 4 mm, right? We've selected 4 mm. Am I right? We've selected 4 mm. Selected 4 mm. So go and let's see what the resistance for 4 mm is. I'm going to my. I want to see this is conductor technical information for single core cable. Its maximum DC resistance is at 20 degrees Celsius. Now let's go. I'm selecting 4 mm. Can you see? Can you see my 4 mm? Yeah. Now this is points. So hello. So I will need to convert it to meter by dividing by what? I will divide by 1,000. So divide this by 1,000. Let's see. So that let's just do this together. Let's do this together. Let's do this. So the formula is the voltage drop will give us what? We already know what our V maximum is. That's I maximum. I divided by 1,000. That will give us 0.00741, right?
Yeah.
All right. 1,000. Right, 9. So now when you multiply and divide, that will give us multiply and divide, that will give us that is the way they measure that. Multiply will give us what? Just 1 4 so that we multiply. Actually, this bar. We multiply and divide, that will give us that's 0.0167. 0.10,000. As soon as 10,000 is 10,000. That will give us what? I'm saying that the distance is 10,000.
I say, is it 10,000 meter?
Yes, 10,000 meter, 10,000 meter.
I got 200.
What's happening?
Hello, can you hear me?
Welcome back.
All right,
Welcome
sorry
back.
for the
Yeah.
network. Wahala, Jare. All right, so let's continue from where we stopped. Share my entire screen. All right, so still on the, you can see the screen, right?
Yes.
All right, so I'm sure you, by now you should know how to calculate the voltage drop. I remember
Yeah.
next to 3. This is the
I
sorry.
missed that. I couldn't follow you.
Which part is that?
The voltage drop you explained.
This I want total input voltage is the voltage that we got from here. We are using V, and we set 16 in series 17, which is 676.09. All right, so this is the current that we are using, 15.34, and it is 100 meter. So using that, the voltage drop is all right. Identify the type, the cable. We've identified the size, which is 4 mm. Identify the length, 100 cable voltage drop from the source, and ensure it doesn't exceed the limits. All right. Now, if it exceeds the cabling on the street, to calculate the power loss as it. This is the formula. There is actually a template. All right, but when we start the other class, all right. Now let's set break of and over electric going forth or shared circuit. So circuit breaker is performing two functions. It trips whenever there is an overload, and whenever there is the same thing I move for fuel. A fuse has an important component, which is a metal wire or strip that melts when it. So once there is an overload, the metal wire or strips will melt the current. It disconnects those, or if there is a short circuit, it melts as well. It disconnects. So these are the two that we use. So right bit back. Then you consult him. So we need one melt. You will need to that is all right, is correct. Forget saying the main thing there is the load current. Now specify the rated voltage used in the system. This for 3 phase. Now calculate the current here. Formula for 3 phase. Multiply the octane of my need is just this short circuit. Once I look at it, all right? Once I look at this short circuit, 16.05, then I can size my breaker with this. I don't need to do any division. I just once I do this, I can size my circuit breaker with this. So now, based on the current obtained, select the appropriate size of the circuit breaker. Current view, for example, now this I have this to be my maximum 2.05. If I size my breaker, now who can tell me what will be my breaker? I'm sure you know that there is no 16.05 in the market. There is in the market, right? 20 amps in the market. So you simply go for size my breaker. I'm sure that 240.3 amps is not in the market. So which one will I go for? I will simply go for what? 250 amps. That's what is in the market. What is the appropriate of 15 kilowatts and choose the appropriate. All right, now you can see it's a single phase. So since it's a single phase, I'll just divide by the voltage. You can see 65. For those of you that do residential, if you're going to size the output cable, remember an inverter has an input terminal, and for that output, just divide. You can see you have 65.2 amps. 65 amps, you multiply it, you can see 81.5 amps is not in the market. The closest one is 100. Breaker of 100 amps to be used for the protection. All right, so now let's see MCB, CB, and ACB. There are different types of it. So now when are you to use MCB, MCCB, and ACB? I'm sure you must have seen this of breaker before. This type is what? What is MCB?
Miniature circuit breaker.
What about this? What is MCCB?
Circuit breaker.
Good, thank you. Miniature circuit breaker, but this one is molded case. Molded case circuit breaker. All right, so what is this one? This one is ACB. What's ACB?
Yes, circuit breaker.
All right, so you can use any of them on the. If I have 10 amps, obviously, MCCB is not make in 10 amps. I'm going to see. So this is it. Miniature circuit breaker. Its rating is from 5 to 8 now. So there is, if you have, for example, now 150 amps, 200 amps. There is no 150 amps MCB. There are no 300 amps MCB. All right. For higher current, then you go for molded case. There is no difference between the three of them. They perform the same function. They are all ends that they can date. So molded case, what is this? If you are seeing a single phase, all right. Now let's move on to DC combiner box. So Oyetunji, please mute your mic. Oyetunji, mute your mic. So now let's move to DC combiner box. A DC combiner panel is an essential component in solar PV system that consolidates the DC output from multiple solar streams to the inverter. It's very simple. That is all. All right. Now, when you look at this now, the DC combiner panel consolidate the DC outputs from I'm connecting 70 series. 17 modules in series. I have, let me just, for example now, I have, this is 17 module. I have 17 module, I have 17 module, I have 17 module, 17. Or I have 1, 2, 3, 4, 5, 6. So this is 17 module in series module or on my roof. All right. So from this 17 module, you are going to have positive and negative, positive and negative, positive and negative, positive and negative, and so on like that. Now the positive and negative of this module will come inside a DC combiner panel, All right. Now in a DC combiner panel, you have a positive breaker, or it can be a fuse. You have negative, all right, and you have a bus bar. You have the main breaker, all right, and you have what is it called? You have a surge protector. So now it helps optimize power transmission, ensure system safety, and simplify maintenance. Helps in maintenance, cycle current of the PV array, all right, and the number of strings. I'm going to tell you that. Now a DC box has a DC fuse box like this. Now this is a DC box. Can you see it? This is a DC fuse box. Can you see it? All right. A neutral link. This is a see it. The neutral can also be connected to a switch. Now you can also see this is a surge protector as well, and the main breaker. You can see this is the main breaker, and this is the main breaker. A surge protector inside the combiner is only a problem. So that is the reason why earthing is very, very key in our PV system. All right. So now let me explain this. Remember, I mentioned to you that for this 17, you are going to have positive and negative. Now, I'm going to use this to explain it. Now, from this 17 module, the positive is that this fuse, while the negative is going to be terminated at this neutral link. Or if you have a breaker, all positive is coming here, Now, for this system now, let me assume that I'm doing this system. I have 17, 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, 5, 6. That fuse, that's 15 fuse box, which is going to be the positive. Now, in this case, look at this example that I have here. Now, when you look at this example now, how many is this? If you can't see 4, 8, 10, 11, 12, 12 here. In this case, how many do you have there? You have 1, 2, 3, 4, 5, 6, 6. But in this one, I have 3, 4, 5, 6. I also have 6. All right. So I'm going to connect the positive to this. At the end of everything, the positive is going to be matched to a bus. The neutral, this is the bus bar for the neutral. Can you see it now? This is the bus bar for the neutral. So there's a bus bar, there's a bus bar. So the bus bar will come to this side. So at the end, I'm going to have a negative, positive, and negative. So if I'm going to size my combiner box now, giving this example, if I'm going to size my combiner box, remember this is 6, all right? Now, what will be the size of the fuse? Each of the fuse will be what? Remember, this is 16. Each of the fuse will be what? I mentioned to you that there is no
20 amps.
There is no 20 amps. All right. I'm going to have 6 of 20 amps. So the positive will terminate in 20 amps. Positive in another 20 amps. Positive in another 20 amps. Positive in another 20 amps, and so on like that. So I'm going to have, this is my, everything will match here. This is my positive positive, positive, positive. This is my combiner box. Then this is my neutral. Then I'll have my neutral thing. Now, what is the name of this breaker here? What's the name of this breaker? You can see now this is what? MCCB. Why are we not using MCB? MCB 16.06. All right? 16.06. That means the current from this one is what? 16.06. Current from this one is 16.06. 16.06. 16.06. 16.06. So what will be the total current?
100.
That is 19.0. So that is simple. I can go for combine one. All right. So instead of using, because the terminal ports for MCB is very, very small. And remember, it also depends on the cable that you are using. All right. So if that is advanced, design this now, I'm going to be using 100 amps. But the 100 amps I'm going to use will be what? MCCB. Because I want everything to, right? Cable as well. So the size of this MCB, sorry, this DC command should be what? 100 amps, sizing the inputs breaker based on the main breaker. So at the end of it, you're going to have positive and negative. So the positive and the negative will just go straight to your inverter. Remember, inverter only has where to go. DC combiner box. I'm sure you should be able to size DC combiner box. Now let's move to the next one, which is AC combiner box. Now an AC combiner panel is electrical panel used in solar power system to combine AC outputs from multiple inverters before feeding transformer. Now, now it's a single point for monitoring and protection. Now let's come to this. Let's come for the AC assume inverter. I have one inverter. Let me assume that I have five inverters. All right. Still on this inverter that I'm explaining to you. Still on this inverter. Now, what is the maximum current of this inverter? Because 240.3. So now, which MCCB can I use? Which MCCB can I use? Oh yeah. Oh, that's I am listening. Can you hear me? Hello.
Please come again.
Now right, and AC combiner box received the output from different inverters. All right. So now I want to design it now. I'm five inverters, and the inverter that I'm using is this inverter. All right, is this inverter. Now looking at this data, the maximum output current of the inverter is what? 240.3. So now which break am I going to use? Which side of break am I going to use? 240.3 is not in the market. So which one am I going to use? I will simply use 250 amps. All right.
Yeah.
That is 250 amps. That's 250 amps. 250 amp and of it, right? I will have a bus bar where all this will come. All right. Now this is 250, and what is the current is 230, right? 230. Now if I have 5 of these, remember, this is how it's recording. This is how a combiner is. Then you are going to have a bus bar. Then you have a main breaker. You're going to have a main breaker. You're going to have a 3-phase bus bar. And if the current of each of these is 230.4, 230.4, what will be the size of the main breaker? What will be someone breaker? Oh, yeah.
1,000 amps.
Sorry?
1,000 amps.
Are you serious? 230.4 plus 230.4 plus 230.4 plus 230.4. Give us 1,152, right? So if you are using 1,000, if you are using 1,000 amps,
That means your breaker will keep on tripping.
thank you. It will keep tripping. The breaker will keep tripping, and once the breaker keeps tripping, there will not be current. Times is 1,000.
1,000.
You can see what, right? So that is how. If I'm looking for this 250 amps AC panel, all right. So you can see this is how it is now. You can see for this installation, I'll say I have 1, 2, 3, 4. I have 4 watts, 4 inverter. Can you see 4 inverter? You can see.
Is there a difference between? Hello, sir.
I can hear you.
Hello.
Yeah, which I can hear you.
Is there a difference between DC breakers and AC breakers?
Yes. The DC breaker should be a breaker that can withstand the voltage. If you are buying any breaker, you check the voltage. Remember, DC breaker different ranges of voltage. DC voltage, you can have a DC voltage of that the maximum is 1,500. Ensure that be a breaker that can withstand that voltage. But for AC breaker, the voltage is just if it is 3-phase, voltage is 400 volts. You understand? So there is a big difference. You know, breaker should be used for AC breaker should be used for DC installation. You understand that? So you can see this, and this is a breaker for lightning to. All right. So now an AC is sized based on the maximum output current of the inverter and the number of inverters. An AC combiner panel has MCCB breaker, bus bar. You can see the bus bars here. You can see the bus bar. A surge protector. You can see the surge protector. And breaker. You can see that here. All right. So now the surge protector inside the panel is only active if there is a proper grounding. It is only active if there is a proper grounding as well. All right. So by as a sense, all right, reducing wiring complexity and improving system reliability. bar is current. Now we have aluminum bus bar. The current density is between 0.8 to 1. The area of a bus bar is sized by the maximum current divided by the current density. Now, if you are sizing a bus bar now, if I'm sizing a bus bar now, I can say this bus bar is 200 amps. I can say this bus bar is 500 amps. How do you know it is 500 amps? Bus bar, there should be a spacing. For phase to phase, 5 millimeter. For space to neutral, you should do 90 meter to avoid interference. All right, to avoid interference. Now let's see the copper board. Combine 5 inverters with maximum output amps, with maximum output of 4 amps. This is it. The total current, since it's 5 inverters, the total current is 435 amps. So that I need. So if you can't see it, you go for higher ones. All right. Now, even if I know the rating of the board, do I size it? All right. How do I size it? Remember, there is like a thickness and a width of. How do you know the thickness? How do you know the maximum current by the current density? All right. So I'm using the least one. I'm using the least one because if I can size for the least one, then it can accommodate for the higher ones, all right? So for copper, the cost is like M. Between this and this, there should be a 19 mm. This is aluminum bus bar. Know how to space it. All right? My cross-section 3 millimeter square. If my cross-sectional area, this is copper. My cross-sectional area millimeter for this type. This is it. This is my size that I'm looking for. The 3. This should be the size. All right, this should be my size. It should be this 50 by 6. 50 by 6. This should be the size. If it is at free air means that if it is outside. Enclosed means that if it's within a, there's a way you can bring your combiner, your bus bar, you put it outside. You are not enclosing it. Like in this case, now these ones are enclosed. All right, these ones are enclosed. So this is for copper bar and aluminum bar. So that is how to size your bus bar. So that is that for the BOS. If you have any question, I'm going to do PVD Zoom. If you have any question, ask your question. We are done with the POS, but there is still more to, like I mentioned, which is the what's it called? Earthing and lighting arrestor. So Emeka, your hand is up. Ask your question. But before you proceed, the we don't want us to stretch this from 12 to 1. Let's do 3 hours today. From 12, let's just do this. All right, so I'm going to take a question now from, this is 11:47. Let's take questions to once. Sorry.
Okay, so good afternoon, Mr. Good morning, Mr. Moses. Sorry, I'm just joining. I hope I've not missed a lot. So I joined at the point where you were talking about the AC combiner box. So I want to clarify something about that. Is it supposed to be called an AC combiner, bearing that is positioned between the PV and before the inverter? That is the combiner box before it goes out to the inverter. So why is it called AC combiner box? Or is that the
the AC combiner box? The reason why it's called AC combiner box is because the current that is inside that box is alternating currents. Load or transformer. You understand? So that's the reason why it's called AC combiner box. The reason why we have the DC combiner box is because it is bringing in the output from the PV module, and what the PV module is supplying is DC current. All right, so it's terminating either at MPPT, that's the charge controller, and you know what the charge controller receives DC. So it is standing between DC and DC, so there is nothing like AC there. So that's why it is called DC combiner. So for AC combiner box, it is standing between the output of your inverter and your client's load. And the output of the inverter is strictly AC. Do you understand it? So that's why it's called AC combiner box.
Oh, okay, very clear. I never knew there was an AC combiner box, so I thought it was just DC combiner box. Okay,
we have DC combiner box, we have AC combiner box.
Okay, that's
let me show you. Can you see my screen? This is it. This is DC. Can you see DC combiner box? This combiner panel, and this is AC combiner panel. All right, Abdurazak, you can go next. Abdurazak, you can go next.
Okay, good sir. Thank you for giving me the opportunity to ask my own question. I have two questions. Okay. I noticed that throughout the class, we've been calculating for voltage. Do I understand that we are in CNI, and basically what we consider most is the voltage, because we know we are using a very higher voltage. But I noticed that we did it basically, maybe based on my own little experience. Okay. I believe that we also consider currents too when sizing, most especially when it comes to the battery and the basically when it comes to the battery. That is question number one. Okay. Then the second question is come to the issue of this combiner box. You know, you're talking about the first calculation that we had when you're talking about sizing a cable for DC. When we say that sometimes we'll have 500 mm, which is very, very difficult. But due to the cost, since it's a business, I'm looking at something that, okay, if you're saying that, okay, 500 volt is very, very heavy to carry, but are we not considering the costs too? Because when we have a bigger cable and we run a single cable to terminate at the end, and maybe having another cable, let's say for example, you are setting an example of meter of 100 meters. Now the cost of 100 meters for like 5 wires and the cost of 500 meters for one wire, is it not something to put into consideration again? Those are my two questions.
All right.
Thank you.
All right, thank you. So let me answer the first question. Now, it's not like we don't talk about current, all right? But the reason why,
yes, sir,
we don't usually use current in our design. The reason why we increase the voltage, and the reason why we are increasing voltage is because where you are terminating either the charge controller or the MPPT of the inverter, they've already stated it there that the current should not exceed a certain value. All right, and this is what it should be. So what we are doing is based on conditions. All right, that is the reason why you need to understand the data sheet of what you are designing before you proceed. If they tell you that this is what the current should be, obviously you will use the current. Yes, and again, if you are considering too much current in your system, there will be a lot of losses from P equals to I squared R. All right, reason why it is mostly voltage. Now I'm going to give you an instance now. Now, some years back, All right, the voltage usually have volts. It is mostly 800 volts, 400 volts. I'm going to the data output voltage